the union would be in tau in X, because if they're already in X, then combining them would still be within X. And so because of that, there should be a Y, open set in Y. That gives us that. So we want to show that there's a B in tau Y such that the intersection of what we have up here is a open set as well. Rats. Okay, I thought I had to go back all the way. So we did that. A1 is the inverse image of B1, and if we're intersecting with A2, that is also equivalent to the inverse image of B2, and we are allowed to move these two in one set of parentheses, and that will hold its same value. So this B will be the intersection of B1 and B2, and we know this is valid because B1 intersection B2 exists in topology Y, and we know that because topology Y is a topology, and B1 and B2 exist in the topology. So therefore, the intersection would also exist. So since the intersection exists, we're allowed to move our way backwards, if you want to start that way, with the inverse image of B1, B2 being allowed to be separated. And then we see that they're equivalent. So we now have that the intersection is a subset of X. So then the intersection is in tau X because they exist in the topology and the intersection also exists in the topology. And the third one, condition says if there is a collection of sets in topology X, then the union of the collection is also in topology X. The last step is if I can't remember if I already said this. If the collection is in the topology, then the union is in the topology. So to rewrite this, I want for all alpha in A, that's just this part right here, for all these, if A sub alpha is in the topology X, that's the rest right there, then the union is also in the topology of X. So we'll start off by letting the alpha be in A, since A alpha is in topology X, then we have that A alpha is a subset of X such that there exists a B alpha and topology y that gave us the inverse image. So A alpha is the inverse image of B. So we've been using that. If there's a B in tau y, you'll get an A in tau x. And I'm going to write one more so we can see. So since A alpha 2 would also exist in topology X, then the same rule would apply. And as you can see, there will exist several B in the topology Y that will give us a set, an open set A within topology X. And with that, we can say, therefore, the union of these alpha and A for A sub alpha is a subset of X, where there exists a B in tau Y such that the union of A alpha for alpha and A is equal to the inverse image of B. And I'm going to share some more rules. So we are allowed to say that this is equivalent to F inverse. I'll switch colors because this is like a side proof. F inverse of the union B alpha, which we are allowed to move that union out. I'll move in this direction. The union alpha F inverse of B alpha, and that is equivalent right here. The inverse is equivalent to A. So we can write union alpha in A for A sub alpha. So we just showed that this is indeed equal to that, as these are the same. And so let me see. So this B is namely the union of B alpha for alpha and A, which exists in tau y, because again, it is a topology. So I'm gonna change colors again because I'm running out of space and I don't want it to be, actually, I'll erase this. It was just to show that they are equal. So then the union of alpha and A for alpha, A sub alpha does exist in tau x. Therefore, we proved all three conditions, and this is a topology for X. So we can write that to show that it's a topology for X. Thank you.